In this course, it's going to be really important to be able to identify whether or not pi electrons are delocalized or centralized at a specific location. The delocalization of pi electrons gives rise to some really cool chemistry that we're going to learn about in this course. Now, in order for pi electrons to be delocalized, they need to be what is called conjugated. So conjugated dienes are going to be two pi bonds separated by a single sigma bond. So in the question that you were provided before this, that I hope you took a chance to see if you could answer, you can see that the first molecule contains 2 pi bonds separated by a single sigma bond. So this is the only sigma bond that separates those 2 pi bonds. Now, this means that this diene is conjugated. And again, it's going to be 2 or more pi bonds separated by 1 sigma bond. So what you should then be able to see is that in the second molecule, we have 2 sigma bonds that separate those 2 different alkenes. Therefore, we would say that these alkenes are isolated. And then finally, the last one has the 2 pi bonds directly adjacent to one another, with no sigma bonds separating those different alkenes. Therefore, we would say that this is cumulated. Previously, you will have learned that a sigma bond is formed via the overlap of 2 atomic orbitals that lie along the bond axis. And you can think of this in simple terms. So a sigma bond is going to be like the overlap of 2 s orbitals. When those electrons share between these 2 orbitals, this ends up looking like an oval, where all of the electron density is located along the internuclear axis between 2 different atoms. A pi bond is different in that instead of the orbital overlap lying along the internuclear axis, instead we have 2 unhybridized p orbitals which overlap above and below the internuclear axis of 2 different atoms. And this allows for the sharing of electrons to occur again above and below the bond axis between 2 different atoms. Now, this orbital density lying above and below the internuclear axis has some special properties that we're going to take advantage of. So take a look at these 2 examples where we have a conjugated diene, again separated by a single sigma bond, and a situation where you have an isolated diene which contains 2 sigma bonds separating the 2. If we were to draw the atomic orbitals involved in these 2 pi bonds, we would see that there would be a p orbital here and a p orbital here. There's also a p orbital here and a p orbital here. Now, if we were to put in our shading so that they're all in phase, indicating a pi bonding orbital, we should see that we have overlap above and below between these 2 atomic orbitals. We also have overlap above and below these 2 atomic orbitals. And finally, we also have overlap between these 2 atomic orbitals. And this overlap allows, just like in a pi bond, electron sharing. So electrons can be shared between those pi molecular orbitals, which means that the electrons contained within these pi bonds are actually delocalized. They are not stagnant, they are not stationary, they are able to move about relatively freely. And because of that, this means that electrons can be shared all within these different locations. So these electrons could be predominantly found at several different locations within this conjugated diene. Whereas if we were to look at the orbitals involved in the pi bonding of these molecules, of this second isolated diene, now we still have some delocalization here, again above and below, but there's a separation between the 2 different dienes where these sigma bonds prevent any delocalization of electrons between this region of the isolated diene and this region of the isolated diene. Effectively, you can think of there as being a node where there's no electrons that can pass through this space because these p orbitals and subsequently the pi orbital that's formed from the molecular orbital do not allow for sharing to occur through multiple sigma bonds, which is why there can only be a single sigma bond separating two different alkenes that allow for what is called conjugation or delocalization of electrons. Previously, you will have learned about addition reactions between alkenes and some other molecule. Now, what happens in this event, just to remind you, is that the electrons located in this pi bond will be acting as a nucleophile for the electrophile proton in HBr. This will kick off the electrons and put them on bromine, which existed as a sigma bond between H and Br. And this is going to add in a Markovnikov fashion. So this means that we are placing this new hydrogen here, leaving behind a carbocation in the most substituted position. So this is going to be the most stable position for this carbocation, which is why you get this regioselectivity. And then you have your bromide anion, which then can come and act as a nucleophile for the electrophile at the carbocation position, giving us a product that looks like this, and I'm indicating the new bonds that have been formed in a different color. Now I want you to think about what might happen in the event where we have a conjugated diene which allows for delocalization or movement of pi electrons. Specifically, I want you to think about an example where you have this specific butadiene, and then we are just adding the same reagent, so HBr. What do you think will be the products? And again, I say products with an S because there are actually two that are formed. I want you to pause the video and see if you can come up with an answer for what products might be formed via this type of addition reaction where you have a conjugated diene. So the first step in this type of reaction is actually the same as the previous addition reaction, where these pi electrons are going to act as a nucleophile for the electrophile proton. The electrons located in that initial sigma bond are going to be kicked over to the bromine species, and this is going to create what you might have predicted, where you are still adding the H at that terminal position. You are creating the more substituted carbocation. However, what happens next can occur via two different pathways. And for this, we need to consider the resonance or the delocalization of these pi electrons and what impact it might have on this structure. So previously, you will have learned about resonance structures where you can move around pi electrons, especially if they're separated only by a single sigma bond. So in this case, what might happen is the pi electrons here can be shared to this position. And this is going to stabilize this structure by forming a new one. So in this case, we have our formed hydrogen bond. The alkene pi electrons have shifted over, so now they are in this position. And because of that, we are still left with our carbocation, except now it's at a terminal position. So what we have done is through resonance, we have created two different resonance structures that are relatively equivalent in energy, and both of them can exist in reality to some degree. Now we know, for example, that the more substituted carbocation is going to be slightly more stable than the terminal carbocation that's formed via this resonance structure. So what that means is that when the bromide comes in to attack, what's actually going to happen is that the faster reaction is going to occur when the bromide attacks at this more substituted position where the carbocation has two R groups, making it a more stable carbocation. So this is a very fast reaction where now we are generating a new product where we have added our H and our Br, And this is because it's so fast, because again, this is a slightly more stable resonance structure. In addition, there doesn't have to be any movement of electrons for this pathway to occur. So because it's so fast, we call that the kinetic product, because it is faster. And in fact, we call this a 1-2 addition. We call the 1-2 addition product the kinetic product because it happens faster. Now, let's consider what might happen with this resonance structure, where we still have our bromide, which can come in, and rather than attacking at this position, it will instead add to this terminal carbocation, forming a product that is actually slightly more stable. So in this scenario, we have generated our two new bonds, and we are left with an internal alkene rather than a terminal or at the end alkene. And even though this carbocation is slightly more stable because it is located at a secondary carbon, this is the more stable alkene, which is more substituted. So the internal alkene is more stable than a terminal alkene. And overall, this molecule is more stable. It has a lower enthalpy of formation. So because this is more stable thermodynamically, we call this product the thermodynamic product. Thermodynamic product. And this type of addition is called 1-4 addition. And it's called 1-4 because this is the 1 carbon, the 2 carbon, the 3 carbon, and the 4 carbon. And previously we called the kinetic product the 1-2 addition because this is the first carbon and this is the second carbon. So it's a 1-2 addition for the kinetic product and a 1-4 addition for the thermodynamic product. Now for this problem, let's first look at two incorrect or wrong answers. So some of you may have predicted that the very first step that might happen is the pi electrons will act as a nucleophile for the electrophile proton, kicking off the bromide, which is absolutely fine. However, if the first intermediate that you were to draw contained a proton at this position, leaving behind a carbocation at this position, this is in fact not correct, because you are not creating what is called an allylic carbocation. So an allyl carbocation is going to be a carbocation that is adjacent to a pi bond. So this is an allyl carbocation, and we call it an allyl carbocation because it can be stabilized by resonance. So we know that these pi electrons can be delocalized, which can move them over to this position, leaving behind another resonance structure. And because we are creating a second resonance structure, this is actually a stabilizing feature. So anytime you can have multiple resonance structure, typically that is going to be a more stable compound or conformation as opposed to one that only has a single resonance structure. And that's the importance. We're looking for the stability of the molecules that are formed. So this one, there are too many sigma bonds separating the pi electrons and the carbocation. Therefore, this product is never going to be formed. Similarly, you might have predicted that the interaction would occur at this pi electron, kicking off these, leaving behind another carbocation where you have added the proton at the position that would create a carbocation here, which means that the hydrogen was placed at this carbon. Now again, what we can see is that there are 1-2 sigma bonds separating this carbocation and the pi electrons. We can only have a single sigma bond though in order for those pi electrons to be conjugated and thus provide us additional resonance structures. Therefore, neither of these intermediates would be the first step in a successful reaction with this conjugated diene. So I want you to again pause the video and see if you can come up with which type of structures might allow for us to form an allylic carbocation that would allow to product formation. We're going to be looking specifically for 3 different products. However, if you come up with 4, you might be on the right path and just not recognize that 2 of those molecules are the exact same. So in the productive pathway, one of the options that lead to us forming an allylic carbocation and thus a successful formation of some desired product is going to be, again, we take these pi electrons, we kick off the electrons to the bromide, and what we generate is going to be an allylic carbocation. So what we are going to generate is the carbocation in this position. We still have our pi electrons, and the new bond that's formed actually happens at this top carbon. Now, what you should be able to see is that we have formed a situation where we can have resonance stabilization of that carbocation. So another resonance structure that could potentially be drawn would be if those pi electrons actually move into this position, that is going to place the pi bond here, leaving behind our carbocation at the bottom carbon, and again, here was where our hydrogen was added. Now we have 2 different positions where bromide could come and add. So I'm going to draw in our electrons, and we can see that there is one product that could form via the attack of the nucleophile bromide at this carbocation position, and then similarly the bromide could come in and act as a nucleophile at this carbon position. This is going to generate 2 different products which look like this, where we have our, sorry, I drew the wrong one. Let me redraw that for you. Where we have product formation I'm going to draw in my new bonds with a different color. So again, the hydrogen is at the top in both of these positions. And now we see that we have bromide at this carbon position, and we have bromine adding at this carbon position. And this gives us 2 unique product formed via this step. However, there is still one more option that we could have generated via this reaction. And I want you to think about this as to what would happen if these were the pi electrons that came and acted as a nucleophile for the proton. So if instead it was these electrons, these pi electrons, what we would generate is going to be a product where we have again generated our carbocation in an allylic position. We have added our hydrogen atom at this bottom carbon position. And again, we have 2 resonance structures that could potentially form here. Again, because these pi electrons are delocalized, they can actually move and generate this new species where we have the carbocation at the top position. We now have our new bonds still at the bottom, but notice that these are 2 distinct structures. So now the bromide ion can either come and attack at this position, or it could attack at this position, depending on which molecule is in your solution. This is going to generate 2 different products. So if it attacks at this position, ortho to the methyl group, then we would generate a product that looks like this. We can't forget our pi electrons here. Or we would generate a product that looks like this. What I want you to notice is that these 2 products are actually the exact same, where you have a methyl group adjacent to a carbon with a bromine on it, so a methyl group with a carbon adjacent to a bromine on it, and in the opposite direction you have this double bond, so in the opposite direction you have this double bond. So these molecules are actually identical. They are not isomers of one another. So what I want you to do is start getting in the habit of pausing the video and trying to work out the problems as we go through them this semester for all of these videos. It's really going to serve you well to try it in advance, and then you can resume the video and check out my explanations.